Okay, so mechanically coupled oscillators. Um, there's a variety of different kinds. I picked like a selection here that I like. They often display emergent phenomena like synchronization. Um, Metronomes are the most popular example. You can start them at arbitrary phase angles, and through mediated force feedback through a shared substrate, they can actually align their phase with one another. We have rowing teams, another team in which the team synchronizes for best performance. Now, these guys are trying to synchronize, but it's actually been shown that this is the stable state. Rowing out of synchrony is actually much harder, and you'll eventually fall back into synchrony. Um, Down here in the middle, this is actually a tiny starfish. And starfish and sled dogs might not seem very similar at first, but what you have here is an organism with a bunch of decentralized legs, no brain. The legs are locally connected to one another, so independent actuators. And what Poe showed was that if you add weight to this little starfish, you can force the legs into synchrony. Um, so no no centralized control here, just decentralized control. These legs will go into synchrony. And then an especially distant example, but another case for gate synchrony is can be seen in C. elegans, which are tiny worms that with the right environmental conditions, you can get them to sync up their swimming behavior. And these worms in particular had their mechanosensation or touch genes silenced. So they don't feel each other and they're still synchronizing. So this is purely through the mechanics of the system. The nervous system isn't necessarily contributing to the synchrony we see here. Um, and then one more just to nail this home. This is a video that Nick Gravish shared with me from UCSD. He did his PhD here. Um, and he's got four little scooting robots. So they've got an oscillatory scooting gate. What they're going to do is they're going to push this large rectangular object together. And what he saw is that just by sharing the load together, these robots will spontaneously synchronize in order to push the load. And he showed that by synchronizing, they're able to push this load faster and further. So my study system, my organisms are sprint sled dogs. They're not your typical sled dog. Their fur is much shorter. They're known as Eurohounds, and they've been bred specifically for the sport of sprint racing. Here I'm going around turning off sensors. Um, each dog in the team is wearing one of these sensors. It's got a box that sits on the shoulders of the dog that measures acceleration. And then near the tail end of the dog, which you'll see here in just a second, we have a load cell that will measure the forces in the tug line. Um, you'll see that on the dog here in just a second. You can see there that load cell splices in between the harness where it would normally connect to the tug line, and we just add a couple inches and a load cell. So the data that we collect from these sprint sled dogs who are at a constant gallop the entire time, it's a fast-paced version of sled dog racing, um, looks like this. This is like 2 seconds of galloping data from a sled dog. And while it looks kind of messy, I promise it's actually a periodic limit cycle. It's just a little sloppy. But the gate is periodic. We're measuring the dynamics of that gate with acceleration, so those signals will also be periodic. Um, and we're going to treat them as if they were limit cycles, which is just any arbitrary closed dynamical loop. Um, and what we want to do is define a phase to describe this. So a phase value just describes where on the limit cycle we are. And once we reduce to a scalar phase value, we can ignore all the complexity here and we can just have a single value that tells us where we are in each stride. Now, when we have a complex limit cycle like this, the easiest way to create a phase representation is to pick a marker event on the stride. We set this as our datum, and anytime the oscillator passes through that marker event, we'll segment the stride and we'll linearly interpolate a phase value between those points. We do that mostly using the z component or the dorsal ventral component of the acceleration. So here we're actually using this sharp peak in the z acceleration and the zero crossing of that value as our marker event. And we're defining a stride to be the subsequence in between these marker events. So each stride is now represented by a single subsequence. And if we have side view video, we can find out how the gate events align with this subsequence. And using this simple formula, we just linearly interpolate a value from 0 to 2 pi over this subsequence. So now we have a phase angle representing each point in the stride, each gate event. And that way we can actually map the gate to a unit circle where each angle is represented by a different angle. So now that we have this technique, we can perform a phase reduction of the entire team. So this is that dorsal ventral acceleration for the entire team, and we can construct a phase diagram. I don't like this plot very much, and I'll tell you why. Each band here represents a single stride, and if this team were to be synchronizing, we'd expect them to line up vertically to have like a nice grid across the screen, and we don't see that. And generally, if we expected some kind of interaction to be taking place, some strong global interaction, we'd hope to see a pattern arise here. Now, human eyes are really good at finding patterns where they don't exist. So we're going to use a quantitative method to see if there are patterns here rather than just looking. What we'll do is we'll compute an order parameter. This is the Kuromoto order parameter. It returns a value between 0 and 1. A value of near 1 indicates that our oscillators are all aligned in time. They're running in stride with one another. And a value less than 1 or near 0 indicates that they're all distributed around the unit circle. Everyone's at a different part of their gate at the same time. And we'll compute this value over the same 10-second segment we have here. And we'll see that our order parameter, which measures coherence, or the degree of synchronization, fluctuates. And it fluctuates well below 1. And this fluctuation is kind of exactly what we would expect if we had a bunch of oscillators with slightly different characteristic frequencies, and they're all just slowly passing one another and not interacting. So this is just a 10-second segment, and it doesn't contain many oscillations. It's not a great data set to draw conclusions from. So what we'll look at is the entire data set that this clip came from. We've got about 12 minutes, 2,000 plus strides, so 2,000 oscillations, and we'll look at the coherence over that entire stretch. And what we see is this pattern continues. We have a fluctuating value that only ever rarely passes values of 0.8, and we'd never see a sustained value. Constant fluctuation. We can conclude from this that the sled dog team doesn't synchronize. We don't see a global synchronization among the team members. Now, that doesn't preclude individuals from interacting or some local interactions. There could be two neighbors that really like each other and want to run together. So to look for these kinds of local interactions, what we're going to do is we're going to focus on dogs with the most similar frequencies. This plot here shows stride frequency distributions for all these dogs in the 10-dog team. And what we find is that there are a few of them that have really similar mean frequencies. And for interaction, this is the ideal case because these dogs have to adapt or compromise very little in order to align their strides with one another. Or in other words, a very weak coupling strength might be enough to get these dogs to phase align with one another. So what we'll do is, conveniently, these dogs are located in the front of the team, so they're also in close proximity to one another. And we will pick a set, just this set, to look at up close. What we'll do is we'll pick a focal individual and its immediate neighbors, its fore, aft, and side neighbors, and we'll look to see if we see any interactions between these individuals. The way we're going to do that is by examining the pairwise phase difference between each of these dogs and the focal. Here I represent pairwise phase difference with fancy phi or var phi. It's just the phase offset between the two strides. So it's how much someone lags or leads behind the other. And then we're going to quantify how stable this value is with a phase locking order parameter, phase locking value, which will give us a value of 0 if our offset is constantly fluctuating between individuals. And it'll give us a value of 1 if our offset is really stable. A really stable offset is indicative of some kind of reciprocal interaction that's enabling that alignment to maintain itself over time. So that's what we're looking for. I'm going to show a plot here of the cumulative phase difference. from the focal dog's perspective. So this zero line is the focal dog's base state. It's looking at how other dogs either advance ahead of it or lag behind it. And what we expect to see here is some drift due to slightly different characteristic frequencies. They'll drift away from one another, and also some diffusion due to noise perturbations in the system. And that's vaguely what we see over this 700-second period where we do diverge in our phase. What we're interested in looking at here are flat sections. Flat sections indicate that our phase offset is mostly constant, and that's where some interaction could be taking place. Now, I can kind of see some sections that look sort of flat, but these don't also have very similar characteristic frequencies. So it's also possible that by chance they're just running in stride with one another for an extended period before they drift apart. So to determine flat segments that are significant, I use a surrogate analysis of data where the correlation has been destroyed or broken. And what I do is I identify what is the maximum phase locking value that I would compute by happenstance of uncorrelated oscillators. And I use that as my threshold. Anything below that could happen by happenstance. And with that threshold, I identify these regions as stronger phase locking than we would expect by chance. So what's interesting is we have like one pair of dogs, the four and the focal dog, are approximately phase locked for like 3 minutes, like it's considerable. And as well as the dog behind. And then there's a tiny gap in the data there that's like a short stop where the team picked the wrong direction, they were stopped and went the other way. And after that event, they never synchronized again, except for this one other dog. And I actually have about double this data for these dogs, but you just see the drift grow and they never phase align again, which could have some interesting reasons why it's happening. It could be that as the run goes on, the dogs get fatigued and they're less willing to compromise their frequency. So you don't see them phase lock except right at the beginning. But I don't know that for certain. Like this is actually 700 seconds is a short run for the dogs. So normally they're running 30 minutes to 2 to 3 hours. So that's still an open question. Now, we observe some synchrony in the team, but it's just partial synchrony. It's transient and doesn't last very long. And we know from a lot of our other mechanically coupled pulling systems that synchrony often offers a benefit. You can sum your forces. That reduces the forces that you feel on yourself, the resistive forces. By pulling together, you don't get any side-to-side forces or wasted energy. And in such an energetically costly task as pulling a sled, it seems like we might want synchrony. But in order to confirm whether that's the case, I built a really simple toy model. Now, I hate slides of equations, and that's what I'm going to show you today. I'm going to try and go over this as intuitively as possible. So I built a really simple toy model where we have a bunch of self-propelled particles, or dogs, that are connected to a mass with basic Coulomb friction, and I connect them in the simplest way possible. I forget about the Alaska hitch and I just crush them down so they're all connected directly to the sled. They're also simulated in one dimension, so we're not worried about any geometric interactions going on. Now, the agents, or the dogs, they each have a position, they have a phase angle of their own, they have a fixed mass, and they importantly have a fixed frequency. Here I'm assuming the dogs are non-adaptive, and this also has the effect that it makes the simulations deterministic. We're not going to have any change throughout. But by making this frequency fixed, I can enforce the degree of cohesion or coherence just by setting the initial phase offset. So if I start a team in synchrony, they're going to end their run in synchrony. The load, or the sled, also has a position and a mass, which we will vary. The dogs produce what I felt was like the simplest periodic force that I could develop. It's like a half rectified sine wave. It's a little more complicated. I have a amplitude modulation, so they produce less force as they go faster. You have to have something to slow them down or they'll just accelerate forever. And then with each time step of our simulation, we use a simple project and correct approach. We project all the agents and entities in the simulation forward as if they weren't connected. And then after we've projected them based on the force, either the propulsive force or a resistive force felt on the sled, we do a correction step. So we check and see if any of the dogs have exceeded their maximum line length. And what we do is we force them back to the sled with an inelastic collision. So any dog with a taut line isn't allowed to move faster than the sled. That's their maximum velocity. So we basically do a momentum balance so that everyone connected to the sled leaves that time step at the same speed. And if we pick a small enough time step, even this first order integration behaves pretty well. So what I do is I simulate these teams for 100 strides. Here the strides are fixed length, so I can use them as my metric of time. And for a synchronized team here, you can see that as I increase the mass, performance decreases. They're pulling this load a much shorter distance. That makes sense. If something's heavy, you're not going to be able to pull it as far. Now, we can also vary the coherence of the team or how synchronized they are. And if we pick just a single mass and have teams with different levels of synchrony pull it, we see that for each step in coherence we get a regular benefit in our pulling performance or how far we can pull the sled. Now, what we're going to do is we are going to sweep across all of these mass values and all of these coherence values to build a full heat map of the dynamics. Ignore the title for a second, we'll get to that. What we see in this diagram is basically three dynamical regimes. We have a stalled regime. That's where the teams, doesn't matter if you're synchronized or not, you're not able to move that load. It's just too heavy. Above the stalled regime, we have what I call a heave regime. This is where teams are actually receiving a regular benefit from synchrony. They're able to sum their forces by being more synchronized, and they're able to overcome larger static friction values. Interestingly, in this heave regime, part of the reason I named it this is motion is intermittent. They're scooting the object. But we see as we get a lighter and lighter load, we eventually escape into an inertial regime where our motion is continuous. And at that point, all the teams perform comparably. They no longer receive a benefit from synchrony. Interestingly, a lot of the literature on pulling and pushing teams has conveniently stuck in the heave regime where you're going to see benefits from synchrony. And our sprint sled dogs, the name of the game is moving as fast as possible with the lightest load possible. So I suspect that our sled dog teams aren't going to receive much benefit from synchronization, at least in terms of their performance. So the musher, at least, doesn't have any selective pressure to make their team synchronize for better performance. Now, that was sled dog phase. We identified the team doesn't synchronize. We do actually see partial synchrony among some individuals. We also learned that synchrony is likely not going to benefit these dogs moving at fast speed. They might benefit dogs moving more slowly, but not the sprint sled dogs we worked with. Now we will shift over to amplitude and look at a slightly different metric for describing their coordination. I have to admit here that the phase value I just talked all about is particularly weak when it comes to sprint sled dogs. And that's because above a critical speed, most quadrupeds and dogs, their stride frequency will plateau. And that's all we're really measuring with phase is frequency. So we should expect minimal variation or variability in our phase as well as our frequency. And if we look at our dog data set, we see the same thing. Because our sprint sled dogs are always galloping, we don't have the ramp, but we do see a very flat plateau of frequency values. And it's honestly kind of impressive that we did see the partial synchrony that we did, because there obviously minimal variability at these speeds. Now, in order to increase in speed, once you've hit your maximum frequency, the only way to do that is by pushing harder. So within the same amount of stride length or stride time, you're going to increase your stride length. You're just going to throw yourself further in the same amount of time. And that's an amplitude metric, which we can't measure with phase, at least our phase. Our phase is just telling us the distance between these vertical bars, and it's ignoring all the information in between where our amplitude information is held. Now, when we are talking about oscillators, amplitude generally refers to the distance an oscillator is from its true limit cycle. Now in sled dogs, we don't know what the true limit cycle is. Like we could take a mean value, but we don't know. It is a sloppy limit cycle. So we're going to take a slightly different approach, and we're actually going to identify coexisting amplitude modes and how the dogs switch between those modes in time. So I first need to tell you guys about gait multi-stability. Canonically, we understand gait switches as being dependent on speed. So you go from a walk to a trot to a gallop. But it's actually more complicated than that. There are speeds at which you can do a trot and a gallop, and you could switch between those all you want. And we refer to situation where you have multiple gaits at your disposal without needing a change in speed or frequency as gait multi-stability. Wilson suggested, he pointed out that dogs have two types of gallop. I didn't tell you guys about that. They actually have 4 types of gallop that they can use. He suggested that a sufficiently large perturbation could get them to shift from one type of gallop to another. And I don't know of a better system to look for that in. We've got dogs that are galloping all the time and they're constantly being perturbed. So in order to identify what kinds of galloping gaits we have in the sled dog team, I just did a labeling analysis on some side view video. I labeled when each foot makes contact with the ground. And from that information, I can construct a stance stride plot or a gait diagram. So here, each rectangle represents a stance period when a foot is in contact with the ground. And by looking at the sequence of these rectangles, we can identify what kind of gait pattern is represented. And what we see from our short analysis of sled dogs is that they're using all the gallops accessible to them. They're using rotary gallops, which has a circular landing pattern of the feet. They're using transverse gallops, which have a crisscross in the middle. And they're using the right and left leading versions of these. So each of these gallops has a mirrored version that's exactly the same. Unfortunately, like it would be amazing to look and see, this is invisible to our phase analysis, and it would be awesome to see if dogs coordinate their stride switches together. Does one dog switching its stride lead another dog to switching its stride? But my video is super limited. It's really hard to get side view video of sled dogs while they're running because you have to hang out from the side of the sled with a camera on a pole. And if a tree comes up, you have to pull your pole back. So I only have like minutes, and you only ever have 1 or 2 dogs in the video, and one is always going to be occluded. So what we need is a way to identify these galloping patterns without labeled video. And luckily for us, all the dogs are wearing accelerometers, and this information is captured in the acceleration trajectory. Now, here you can see there are 4 gait patterns available, and this was constructed with labeled data. It's actually really hard to by eye which gait pattern is which. It's hard to label. So what I do is I use an unsupervised clustering approach where I don't need labels. I'm just identifying dynamical modes in the acceleration data that represent different gait patterns. And I do that using a segment embed cluster approach. We segment the strides exactly how we did for phase analysis. And then we identify how similar or dissimilar each stride subsequence is based on their distance from one another in acceleration space. And then we'll embed and cluster that information to group individual strides into classes or families that are most dynamically similar to one another. If we do this for one dog and look at those clustered values temporally, this looks a lot like what we see in behavioral ethology as behavioral syllables, which are fixed recurring behavioral states. Here we're just going to call them stride syllables. But we see that this dog over about 20 seconds actually goes through 5 different acceleration modes. Now, I told you before, there's only 4 accessible gait patterns, and that's more. But what we actually have are transitionary strides. Some states only ever get entered, some stable states only ever get entered by a transitionary stride between the two. Unfortunately, there's a little hang up here is that all of these syllables are dog specific. So I can't compare them between dogs. Cluster labels don't line up between embeddings. So I need a way to compare between dogs, and I do that by converting this syllable sequence into a binary switch sequence. So any stride that is followed by a stride from a different cluster gets labeled as transitionary. And now that I have binary sequences for each dog, I can compare between individuals. I should also just be super clear that these dynamical families or classes, we don't know what gait they represent. If we have labeled data, we can find out, but when we don't have labeled data, we don't know. What we do know is they are dynamically distinct and recurrent. So I'm going to show you guys a raster plot of gait switches across the team. If you've ever seen a neuron or a neural spike raster plot, this is going to look exactly the same. Each dog gets a row, and we'll plot a point every single time that they switch their gait. And what we can immediately tell is that there are a lot of gait switches. The sled dogs are switching their gait regularly throughout the run, even when they're at a fixed speed. And we also have a lot of variability between individuals. You might see dog number 8 didn't switch a single time in a 100-second period, where other dogs are switching all the time. We can borrow some more from the neuroscience literature, so we can define the activity of this group of dogs as the number of switches per second. On average, we see about 7 switches per second across the team. Each dog makes about 3 strides per second, so that lowers how shocking this is a little bit, but it's still a lot of switches. Like anytime you look at the team, you're going to be observing a switch. And then from this activity value, we can also compute the phono factor. Phono factor, I borrowed this from neuroscience as well, describes how random these switches are relative to one another. A value of 1 indicates that it's like a Poisson process. They appear to be independent, but a value of 1 or a value greater than 1 indicates that they're more closely aligned than we would expect by happenstance. What we find is a mean value near 1, slightly greater, but not strongly so. That would make us suspect that they are coordinating these switches across the team. And we can also look at the dog variability, which is pretty striking. We do that by looking at the switch fraction, which is how many of their strides were transitionary. We see some dogs, like dog number 5, the orange rectangle, they switch almost every other stride. Like their gait is made up of constantly splicing different gait patterns together, where dog number 8 hardly ever switch. They maintain stable states throughout. And then I also compute dwell time variability. This tells us how bursty these switch events are. Dwell time is the amount of time that we maintain in a stable gait cycle. And if we look at the coefficient of variation of that, it will tell us whether those appear at a pseudo-random amount, or a value of 1 indicates that it's non-random. We're getting bursty switches where a dog will maintain a single state for a long time, and then it'll switch rapidly between a few other syllables or gait types. Now, that's it for sled dog amplitude. We found that the sled dogs do way more gait switching than we would have expected, especially with the canonical knowledge that we should just have one gait pattern. They're also highly variable, and it doesn't appear that these switches are coordinated immediately across dogs. In some ways, the sled dog team is kind of impressive that we observe such strong coordination, obviously, as they pull things together, but they're actually assembled of like such variable individuals. Now, I'm going to shift over to a slightly different project. I'm going to try and go through it pretty quick. So I can, this is the surprise feature film, The Slow and the Subtlest, where we'll talk about cows and how they can form patterns, or I'll try and at least convince you how they can form patterns. Specifically, we'll look at how grazing agents drive terraset formation on steep hill slopes. Now, Saad mentioned this. I went to a workshop in Germany for collective behavior where I was supposed to be working on sled dog stuff. And I took one of the weekends off to go hike in the Alps, perks of grad school. And while I was there, I couldn't help noticing But on all the hill slopes, there are these ridges all over the place. So I spent my hike thinking about where are these ridges coming from. And on my way back to the workshop, I kept noticing these patterns everywhere. They were all over the place. They weren't just in the Alps. Um, and when I got back to the workshop, I hopped on Google and I found out that these are called terracets or little terraces. And their origins have been a matter of debate for like a century. Um, there's two major teams. There's one team that argues that these are biogenic. They're created by trampling animals that will stomp these into the terrain. And then there's the biophysical team that argues that terracets are purely a result of natural geophysical processes like soil creep or solifluction, which can also create repeated patterns in the landscape. Now, this geophysical orthodoxy, I didn't come up with this term. I saw someone else use it and I liked it a lot. Um, has kind of like taken over in terracets. So you get class slides like this that show a picture of terracets specifically to describe what soil creep is. And I feel like it's a little bit deceiving because like the animals are right there. I feel like they should be mentioned as a potential cause. Um, and I think there's some major opponents to the biogenic theory of Vincent and Clark. And they said, I think they hit the nail on the head with their belief was that their data showed clear periodicities, which were hard to reconcile with the haphazard grazing paths of animals. And I might be in a little bit of an echo chamber, but I happen to know that animals make patterns all the time. And I'm figured that certainly cows could make patterns in the right conditions. Um, now, no one has yet given a mechanism for how the cows could create patterns. They've shown like they put sheep on a hill with no terracets and they came back 6 weeks later and there were terracets there, but they didn't tell us how it happened. Um, so while I was at this workshop, I took it upon myself to make an agent-based model to explain how these agents could make terracets. So I built a really simple, well, it's not simple anymore, it got complex, but I have the most simple landscape possible. I have an inclined plane as my hill, and I put a spherical cow basically on that hill, like a super simple agent. And at every time step, it's gonna start a random walk by moving a fixed distance L in a certain direction. And at every time step, it's going to stomp spherical footprints into the surface. It's gonna slowly erode away that surface. And at the same time, it's also gonna consume resources on the surface. So we have two coexisting layers. One is an erosion or height map, and the other one describes how much resource is available where the cows just were. Um, now, what I do is the important part, this is how they modify the landscape. The important part is how they pick directions on the landscape. And in order to pick directions, I give our agents two goals. The first is to maximize their resource intake. This is like a basic optimal foraging piece. Like it's necessary to uh, knock off your maintenance costs, like cost of horizontal motion, cost of metabolism, digestion, chewing. So you have to constantly be bringing in resource. Um, and then also our agents want to minimize their elevation change. If you can get resource without going uphill or downhill, you're just going to walk in a straight line because that's the most energetically efficient route. So I also use a periodic boundary condition on these landscapes. So if our cow walks off the edge of the landscape, they're just going to reappear on the other side. This just makes it so I don't have to simulate a huge landscape. I can do a really finite one. And I encode this optimal foraging strategy by giving them an energetic cost to get to any location, a per step energy cost. Um, Both the resource layer and the height map contribute to this energy cost. So it's got two components. It's got a maintenance cost that is offset by eating resources. If you're in an area with plentiful resources, your maintenance cost is effectively nullified. But we have a vertical cost, which is just based on the absolute distance you have to travel up or down to get from point A to point B. We sum these together, all these per step energy costs, to find out how costly it would be to get in any direction from your current position. And then the key part is we allow our agents to pick the direction from a probability distribution. So it's a random walk. and we bias this probability distribution towards the most energetically efficient routes. And we primarily do that with this beta term. This scales our energetic sensitivity, or how biased this distribution is. By changing the value of beta, we can change the random walk dynamics. So we go from beta equals 0, means that all directions are equally likely to be chosen. They're all equally costly. We get a uniform random walk. As we increase beta, we drive more persistent motion as the agents are trying to head in the most energetically efficient path. And you see, as we start to get to large values of beta, agents are extremely biased towards cross-slope motion, where they don't have to go up or down the hill. Now, with this model, can we create terrasets? This is a time lapse of 3 agents eroding a hill slope, and they're all energetically sensitive. And I don't know about you guys, but these look like pretty good terrasets to me. So we find that, yeah, they can create periodic patterns with the right optimal foraging strategy. We learned that you need adequate slope and an adequate sensitivity to that slope in order to generate terrasets. Here, this order parameter represents how terracety the surface is. It's basically how periodic the surface is. And we find that we can actually make a bunch of different patterns with this model, depending on slope and sensitivity. On the far left there, we have a 0-degree case where we have a flat surface, but our agents are still energetically sensitive. And what we find in this case is that they form meandering trails. And then they use those trails because once they get stuck in a trough, they don't want to spend energy to get out of it. And we can find similar landforms made by animals. On intermediate slopes, we get something where certainly the surface is more anisotropic. It's less random, and we've got biased motion, but we wouldn't call them terrasets. They're not perfectly periodic. And then as we increase the slope even more, we see these periodic bands emerge where agents are not going to use any up or down slope motion unless they have to leave for new resource and move up or down the slope. Right, so that's the end of the research. We saw how sled dogs, despite looking very coordinated and being coordinated, they hide a lot of variability. And we saw how cows, despite looking very variable, actually hide a lot of coordination. I'll point out some of the things I've been able to contribute to over the course of my PhD. Obviously, sled dogs, most of the work you've seen here is still a work in progress. Terrasets actually just got accepted earlier this week with revisions. Thanks. When I started here, I was working on the camera traps, and I worked generally on a couple projects related to conservation technology with Andrew. I've worked on flamingos with Victor. I've helped Saad with building some low-cost hearing aids, and then some other work on elephant trunks, otter paws, normal things. I need to give some particular credit to a number of individuals. On the upper left, I have kind of my conservation team. Got Andrew, who I worked with when I was an undergrad at Georgia Tech, and then continued to work with him in grad school, where we ran a conservation technology course for undergrads together. We have Joe Mendelson, who's like the best resource for an engineer interested in animals to have ever. We're very lucky to have him at Georgia Tech. Jeff Gallus, who's one of our field collaborators in Peru, who has offered me a lot of advice on my camera trap project, and Mexico, an undergrad I've been working with to push camera trap along while I work on all these other projects. There's a couple research scientists and postdocs in the Baumla lab that I need to thank. In particular, Victor for tagging along with me and looking at flamingos and other organisms together, and Atanu and Tuhin, my Baumla lab collective behavior colleagues. Thank you guys for all your feedback and guidance. And lastly, I have my own sled dog team that I need to thank. I have to give a huge shout out to Betcha Ketcha Kennel, Ken and Lori, literally opened their doors for me and let me come live with them for months and taught me everything I know about sled dogs. Um, and they couldn't have been nicer the entire time. I need to thank my committee member, Heather, who introduced me to Ken and Lori, and has a very interesting perspective as an academic who also raced sled dogs. So I'm super appreciative to have her on my committee. Um, I have Zhenyu and Jiayu, my collaborators from Syracuse, who found something to do with the sled dog data that I collected. And last year, I have Matt. Sada introduced me to Matt early in my PhD, and Matt volunteered like way too much of his time helping me. Um, he's the one who put me on to oscillators. He's kind of my data science guru, um, and he's like the nicest, smartest person I ever met. I hope I can repay the favor to Matt someday for all the help he's given me. Um, there are a number of other people I need to thank um, for all the time we shared during the PhD. Um, I want to thank my committee members for your guidance and the time you've invested. I want to thank my advisors. Uh, Thank you, Will, for letting me into QBIOS. It was absolutely the place I needed to be. I know we don't talk as much as we should, but the talks we have had have been incredibly impactful, and I really appreciate having you as a resource. Um, Sod. Uh, Thank you for being so receptive to my curiosities. You've always been incredibly supportive. You've always fought my pessimism with optimism. I think we've got a great yin and yang thing where we create amazing science by balancing each other out. Um, Thank you. You literally have sent me around the world to pursue those curiosities. I should thank NSF for that as well. Uh, but you wrote the grants. So thank you, Saad. I feel very fortunate to have run into you when I did and to have worked with you all these years. And I hope I wasn't too much trouble.
Not at all.
Um, to all my lab mates, new and old, thank you guys for making the Bonla lab such a fun place to work. Um, Thank you for all the feedback over the years, the emotional support, all the intellectual conversations we've been able to have. That was my favorite part. Um, let's see who else. I need to thank my partner Sanj, who originally convinced me to submit grad school applications. It's technically her fault I did any of this. And throughout the process, even when I've been like a huge curmudgeon and very stressed out, she's always been uh, always giving me constant encouragement. And I couldn't have done it without her. Um, to my parents who are here today, um, thank you guys for always being supportive of the things I'm interested in, even when it's like weird and I say I want to go study sled dogs or not get a real job. And you guys instilled in me an intrinsic nature and a love for animals that I relied on heavily throughout this whole process. So I couldn't have done it without you either. Um, and lastly, I'd like to sincerely thank all the dogs who put their bodies on the line so I could put a thesis together. Um, any questions? Cedric.
That was an amazing talk. I really appreciate that. I have a question about the terracing.
Yep.
Terracets. In the last picture you have simulated images, I believe, with actual landscapes.
Yep.
And I'm curious as if you were to find any information about the angle of the actual landscapes, to see if they're similar to the angle that you simulated.
Yeah. I think the ideal, so like I actually created a whole like new order parameter to describe how terracetted a surface is. And the ideal case would be to take that order parameter and apply it to real landscapes to actually have a one-for-one comparison between the landscapes. So it, the ideal next step for this work would to actually put tracking collars on the organisms and find out what their real movement rules are. Because we do have a lot of models for grazing animals, but all of them pretty much assume a flat surface. And there is no random walker model for grazers on a sloped surface, just because it adds an additional complexity that isn't respected well by like a uniform probability distribution. Um, so I agree with you that we should go measure real landscapes. That would be the ultimate conclusion.
Because it looks like it's the smoking gun, and if you just had that angle,
Yep. Yeah.
it's super amazing work. I really appreciate it.
Thank you. Chris?
Beautiful work, Ben.
Thanks.
I had a question about the gate syllables that you had.
Yep.
So you did like an untrained model and something model.
Yeah. Yeah.
How do you know how long the syllables are? And have you looked into like multi-syllabic like gates or anything like that?
Yeah. So I haven't, and I actually, it's kind of limited the way I do it. I generally, when you do one of these segment embed cluster approaches, you're just going to segment. Sometimes it's an arbitrary segmentation size. You don't know when your event starts or ends. I'm lucky enough that I kind of do know when the stride starts and ends, so I can use that. But in reality, I don't know where in the stride they transition from one gate to another. It's unlikely to occur on the event marker that I picked. So a better improvement to this would be to identify or use segments of varying lengths to identify more closely where those switches occur. And then, as you mentioned, looking at the patterns that might emerge in a dog's gait, I haven't looked at. There's some interesting work on fireflies that have like different blinking patterns, and carrying that analysis over to the switching would be an interesting thing to do.
Super cool. Thanks.
Sure. Rajas?
Thanks, Bill. That was really lovely. I especially loved the phase plot where you go from stall to heave.
Yeah, yeah.
Herschel, that was lovely. Yeah, I really put it all together about the synchronization. That was really good. So I have two questions for you. One simple one and one slightly less simple one.
Okay.
The simple one is, is there a job like do sled dogs have a job today? Like, are they like given the existence of snowmobiles or whatever? Like for forever, like they had a job, but do they still have a job, or are they only for sport?
There are a couple of very rare places where sled dogs are still used, but generally the combustion engine has made sled dogs obsolete. Also, sled dogs are just difficult. Like you have to devote your life to sled dogs, but you don't have to devote your life to your snowmobile. So, in traditional use cases, the snowmobile has taken over, certainly. So the only place you'll reliably see sled dogs now is in the sport of sled dog racing. So purely for sport. And the hard question?
Okay, slightly less simple questions. With the embed approach,
Yep.
I'm trying to understand your embedding approach. I'm trying to
Yeah,
understand.
I breezed over that.
Huh?
I breezed over that. Sorry.
So I'm trying to. So did you try when you did multiple dogs? Did you always see 5 clusters?
No. Different dogs use different amounts of clusters.
Sure, but like, do they all have 5 clusters?
No, different amounts.
Different amounts of clusters. Okay.
Yeah. So some have like 3 clusters, some have like 6. So actually, you could make that embedding work across dogs if you embedded all the dogs at the same time, but the embedding does what it's good at, and it identifies strides that are unique to one another, most similar. And what it'll actually do is separate dogs out. So the dogs are all biomechanically distinct enough that their own amplitude modes don't reflect the amplitude modes of other dogs very well. We can a little bit discern between left and right leading gaits because that's like the dominant piece of the dynamics that come out. So we could say, oh, the dogs are left leading now, all the dogs are right leading. But there's quite a bit of variability in how many syllables that each dog has in their repertoire.
It's interesting. The part of the reason I ask is because I work on those embeddings. I work on techniques for that embedding, and I basically there are limitations with. I don't know if you used UMAP.
I use UMAP. Yep.
So there are limitations that are documented where there are clusters that exist that do not get well separated by UMAP.
Yeah.
And conversely, there are separate clusters that get smushed together. Well, okay, you get what I'm saying. It does mix it up. I'm
gonna show you something in all my backup slides. So these are all my stride subsegments that I've aligned with phase. And I embed that with UMAP. Like you said, I have matrix that represents how similar each one of these subsequences are. And if I color them by their cluster, you can see how they separate out. There's certainly some room for some mislabels here, but generally once you've labeled these, especially in the X direction, you can see how the actual different modes braid differently together. So we can validate it a little bit by saying, yeah, obviously that group looks like a group by eye, but there's certainly some strides that are maybe combined. We could have combined groups that are too similar.
You could have combined groups and you can have groups that are similar get separated. Both happen with human.
Yeah.
But it does look pretty robust.
It is pretty robust. I have done it with labeled data as well, so I know what gate patterns are available. I get like 96% labeling accuracy. Like 1 or 2 strides might get labeled in another group, but pretty good. There it's not accuracy, it's like purity. How pure are the groups or the classes that I define? But that's with a pretty limited data set. That's like a dog who only ever expressed 3 gates. So across dogs, that confidence starts to wear down a little bit.
That's really beautiful. Like this is fantastic. And I really like the unsupervised clustering approach for finding these gates and how well it worked. That was really nice.
Yeah, I'm sad I didn't show you guys this one because this is like my favorite part. I think
Ben?
maybe one more
Oh.
question. I don't know how much time. We're over the hour mark.
Can you hear me?
Yes, Andrew.
Hello. Thank you, Ben. I have 2 quick questions. The first question is, so one of the comparisons that you made for your sled dogs was like rowing. And
Yep.
I know that a rowing team is arranged differently at different parts of the boat. So I was curious, when you were looking at some of like the nodal analysis and synchronization, did you see dogs that were located in a particular part of the team that had more or less synchronization?
Well, so in general, it's a great question. Certainly, the sled dog team is structured in a intentional way, similar to the rowing team. Like I know in the rowing team, the person in the front of the boat is the stroke seat, and everyone watches them because they have the nicest stroke and they can synchronize with that person. In the sled dog team, it's mostly structured based on reliability. You put the dogs you trust the most to listen to you at the front because they guide the rest of the team. Now,
Okay.
from my data set, I don't necessarily see more coordination at the front of the team. I did in this team, but that's primarily because they had the closest stride frequencies. I do think that there's some interesting things that happen in the sled dog team. So you have this massive load at the back of the team that can effectively absorb perturbations. And the further you are from this load, the more flexibility you have. Like it's easier to pull your lines left and right if you're at the front of
Yeah.
the team than at the back of the team. So I would expect dogs at the front of the team to have potentially more flexibility to synchronize with one another.
Great. Can I ask one more question?
Yes.
So you got your mechanical engineering degree and finished your ME degree doing a senior design project on cows.
Yep.
And now fast forward a few years and you work a lot with biologists. What is one of the things that you think you've learned about working on these very interdisciplinary teams through your PhD?
Oh, I've learned I'm not a very good engineer anymore. Like, I can't reliably answer engineering questions because I've swapped that knowledge out. Generally, I don't think we're all that dissimilar, the biologists and the engineers. Or maybe I'm just an oddball who's neither one now. I'm always so tickled to work with biologists because biologists have like all these amazing ideas, and that's like one of the beautiful parts of working in the Baumla lab is we have a diversity of individuals who interact, and we're constantly sharing ideas, strategies, finding analogies between systems that would have otherwise not come across as obvious. I don't know if that answers your question. That might have just been me rambling.
It was a great ramble. Appreciate it,
Okay,
Ben.
thanks, Andrew. Anybody else?
Find any messages?
No message questions.
Ben, I've got one for you.
Okay.
Do people actually say mush when they're driving these sleds?
No, nobody says that.
The musher doesn't
No,
say mush.
no, mushers don't say mush.
All right. Well, because my next question was going to be, does the human being and their instructions to the dogs, could that lead to a momentary synchronization? And what is the human role in all of this?
Yeah, yeah. So I like to describe sled dog. So mushers also go by sled dog drivers. That's like the more casual name because it's kind of
Not
funny
as
to just
cool.
describe yourself as a musher. Um, and they do use verbal control on the dogs, but the musher or driver behaves more like a backseat driver. If the dogs know the trail and they run a typical routine, you don't even have to give them commands. They'll run it. There's some fun examples from the Iditarod, which is like the most intense long distance sled dog race in the world, where the driver fell asleep and fell off the sled, and the dogs show up like 60 miles at the next checkpoint with the driver. So the dogs are effectively autonomous. You've just got a backseat driver there making sure nothing goes wrong. So when you're driving a sled dog team, you're constantly just scanning up and down the team looking for potential failure points, yelling at certain dogs who are misbehaving, making sure that they're going to take the turn. There is actually what I learned working with sled dogs. One strategy, like if your dogs are used to taking a right turn at a regular spot, um, and you want them to go left today, you know they're going to be resistant to that change. They're not necessarily going to go left when you tell them to go left. So one of the strategies is to hit the brakes a couple times to give them a mechanical stimulus that you're trying to share information with them. So you're using more than one information channel to make contact with the dogs. I don't know for certain if that actually helps the turn get made, but it's intuitive. Um, there's also the driver is pretty much ultimate control when it comes to starting and stopping the team. And in that way, they do control behavioral synchrony. Like if they want the team to stop, they can apply the brakes until some threshold is met and the dogs become sensitive to it and they will stop running. So in that way, they do synchronize the dogs, but not in terms of their gait. I hope that answered your question.
Yeah, perfect. Thank you.
All right, one more question. This is awesome. Thank you.
Thanks.
I've never thought so much about sled dogs, and now I have a zillion questions.
Okay.
Because I'm curious about how what's the variability in terms of how these sled dogs are organized? Is it always 10? Why is it
Yeah.
not 3 rows? And how did it evolve to sort of converge on
Yeah.
what are the best rules?
This is a great engineer question. And one of my initial curiosities with my dogs, like there are a couple hitches that are known. There's the fan hitch, which I kind of simulated in my simple model, which is like the most primitive way to connect dogs to a sled is you just give each one a line and tell it to pull load. You've got the Alaska hitch, which was developed to go down skinny trails because the fan hitch doesn't go through forest very well. It works great on the tundra where you're not going to get wrapped around anything. And then there's also some other hitches where you have like single tandem lines without pairs. Generally, there's a cool thing about the way that the Alaska hitch works is that dogs can't ever be pulled forward by one another. They can only be pulled backwards because they're all attached to a main line separately rather than to the next dog in front of them. Where some of those single tandem hitches that aren't used anymore have the dogs can be pulled forward, which could, a forward pull versus backward pull could be more uncomfortable, lead to more instability. That's my assumption. I haven't tested that, but and all of these hitches are just tried and true. No one's ever simulated different topologies to see which one would be the most effective. So we've got like thousands of years of I use this strategy, which is really interesting. And there's certainly an analysis that could be done to find out which harness yoke hitch topology would actually be the most efficient. It's a really great question.
This concludes the public portion of Ben's thesis. The next 45 minutes to an hour will be closed room with the committee members, but let's thank Ben again.
Thank you, everybody.
Lab members in an hour or so will join for celebrations. Mom and dad, hang around, don't leave yet. Yeah, Thank you, everybody. Grab some food on your way.
Good luck, Ben.
Thank you, Andrew. Um, unfortunately, that means everybody in the Zoom also has to go.
I can't think for it.
My grad students.
Okay.
What are you? You getting coffee? Bush, back to the left.
When there's the will, there's the
That's
way. Amazing. You know, when he was a little kid, he would
Nest.
Heather, we're just still clearing out the room a little bit. We'll went to
No problem.
get some water.
They wanted to make it rust proof. So that was an engineering. That was not really, well, I guess you had to study what would make that out of not want to go in there.
Yeah.
But like the Okefenokee Swamp, we've camped there and alligators go into
I
hibernation.
did. I'm gonna stop recording now.
They'll run right up to your